Good afternoon, everyone. Thank you for tuning in to my outstanding early career scientist presentation. And my goal of the coming 10 minutes is to tell you a little bit to give you an overview of the latest work that we've done on bivalve shell chemistry and their use as high-resolution paleoclimate recorders. But before I start, I'd like to say thanks to a few people. First, of course, thanks to SSP for this amazing opportunity to give me the Outstanding Early Career Award. It's a great honor. I was really happy with it. Really surprised. I want to give special thanks to Nicolas Thibault, who nominated me and who has been very supportive of my work for years now. So thank you, Nicolas. I also want to say thanks to the FWO and Marie Curie, the European Commission, who funded this research that I will present to you, and of course to all my collaborators, which you'll see on the right side of the screen right here. So they're all. This is a team effort, so I'm just presenting an overview of all this work. I want to start with what I mean with high-resolution climate reconstruction. Well, we all know that we need to understand how warmer climates work because, of course, we're heading towards warmer climates due to the CO2 emissions of the anthropogenic CO2 emissions. And to do so, we have to look into the past, times when it was warmer. The problem is, of course, if we go further back in time, it becomes increasingly hard to resolve climates in the short term. So this is unfortunate because, as you see on the right here on the screen, you see that the short-term variability in climate is actually some of the strongest cycles in climate take place in the shorter term. So we're talking about tides and days and this type of variability in seasons, and it's really hard to reconstruct this. So we need good archives to record this type of variability during climates when it was a lot warmer to see if we can predict or improve our predictions of future extreme seasonality and extreme weather events. One of the ideal archives for this is bivalve shells, and they are known to faithfully record seasonal temperature variability, and their shells are often marked by daily or even tidal rhythms. In my current postdoc project, which builds on my PhD work, I aim to improve the understanding of bivalve shell chemistry and improve this valuable archive through several means. We culture live bivalves to understand how their chemistry is related to the environment in which they grow. We do high-resolution measurements of the shell chemistry. I've developed several statistical routines to get more information out of these records. And last but not least, I'm at Utrecht University applying the clumped isotope methods for absolute accurate temperature reconstructions in the past on the seasonal scale to see if we can learn more about short-term climate variability. So I'll give you an overview of these four aspects of my work in the coming minutes. First, the growth experiments. To understand bivalves as a climate archive, we must study the modern specimens. So in collaboration with colleagues at the Royal Dutch Institute for Sea Research, I actually culture live specimens of different types of bivalves in culture stations to understand their chemistry. And we label the bivalve shells with higher concentration of strontium, as you see here on the bottom left, to mark the time, and then we can later find back how their chemistry related to their environment. In choosing the right specimens for this work, we're selecting specimens that produce different shell mineralogy, so calcite versus aragonite, and some do both, like the blue mussel. We also choose specimens that are represented in the fossil records, such as oysters or also the Arctica type species. And we're trying to find out if different microstructures in the shells or different types of aragonite or calcite influence the results. To give you an impression of what these culture experiments look like, I have a little video. I hope it will come through. So here you see what it looks like inside. I'm not sure the sound is working. You see we keep these bivalves in these aquaria here, which are fed with this microalgae solution. There you see the little oysters. And there's the setup with different bins where you can control different conditions, temperature, for example, and have an idea of how these conditions influence the shell chemistry, and therefore learn how we can use these shells as archives for paleo reconstructions. Oh, we've seen that already. Let me see if I can go back to the slide control. Yep, there we are. Another aspect of this work is trying to devise modeling or statistical routines to get the most out of these records. One thing that's very important when you're working with fossils and you're getting high resolution information, you need to know internal age of these shells. So we need to know the chronology. And there's often markings of the age, like seasonal markings or tidal markings. But to interpret subannual scale variability, we need to know which season we are. And also in case where these markings are not there, often oyster shells don't have these markings. So what I did is based on previous work from Emily Judd, which is cited here as well, I developed a model that approximates the oxygen isotope curve, which very faithfully represents the seasonal cycle, using a combination of a growth rate and temperature sinusoid, and it creates these nice age models of length in the shell versus age of the growth in its life history. And we can use this model then to put the measurements that we do in the shell, superimpose them on the time, and then get an idea of how they change through the seasons. So this model is now available as an R package. So if you're interested in this type of work, you can use it. It's free online. So another aspect of this work is high-resolution chemical analysis. So last year we published a study in which we studied the chemistry of daily growth lamina in these fossil reduced shells, so the old late Cretaceous bivalves, which grew in reef-like structures. And it gives some very interesting results. And we investigated whether the day-night rhythms in these shells could actually give us some clues about not only the Earth-Moon distance, for example, number of days in the year is important, but also about whether these shells hold photosymbionts or whether we can use them to reconstruct things at the scale of even weather patterns. So there's a lot of ongoing work in this direction, but we don't know that much about how shells mineralize at these scales. So for another study, we're now looking at modern bivalve shells where we can control the living environment a little bit better. Looking at both pecten shells and trudecnids, so giant clams, and we're doing the same type of high-resolution chemical analysis to investigate whether similar patterns of daily or even tidal chemistry are recorded in these shells. I'll present the first results of this study in my VPCO next week, which you see a reference of here. So you have to stay tuned a little bit for all the information, but I can already promise that we can actually resolve tidal changes in chemistry in these shells, which is a very exciting result. So I hope to find out more about that soon. Another thing that I've been busy with is clumped isotope work. So for some of you probably know already that the clumped isotope thermometer is a very interesting paleo temperature proxy, which is unlike the stable oxygen isotope thermometer, is not dependent on the composition of the seawater. And it's very interesting that we can use this because we can use this to independently reconstruct seasonal temperature variability if we can apply it on the seasonal scale. The difficulty with the clumped isotope method is that we require a bit more material to do a measurement. So my colleagues and I tested several methods to optimize the number of samples that we need from one of these shells. And you can imagine if we require more material, it will smooth out the record of the seasonality, and it will obscure the seasonal signal. So there are several ways to go about this. We can take small samples for the clump and then combine them in different ways to get good temperature estimates of winter and summer temperature. And we can do this by smoothing, for example, smoothing out the record. We can do this by binning, taking the same parts of the record and putting them together. And we also devised a new type of sample size optimization routine, which works very well, where we actually take sample sizes from the summer and winter side of the record, of the clumped isotope record, and then combine them in an optimal way, where we make the optimal compromise between large sample sizes, so small error bars, and still defining the winter and summer seasons. And we tested these three different methods on a range of virtual and real data sets to test which one worked better, and the optimization routine actually performs quite well. Another caveat of clumped isotope work is that we don't yet have a very solid idea of whether there's a difference between different mineralogies in the clumped isotope thermometer, so different between aragonite and calcite. So we measured some of these Arctica, Icelandica, aragonitic bivalves from our culture experiments, and to show that the aragonite relationship between clumped isotopes and temperature is very close to the one that we know from the calcites, which is published in all these calibration records. So that means that we can use it. That's very good. One application of this clumped isotope seasonality work was done in this very nice site from southern Sweden, the Kristianstad Basin. From this from the late Cretaceous, here we have very nice bivalves that are well preserved, and they show that the seasonality, if we apply the clumped isotope method, the seasonality is actually quite pronounced in this late Cretaceous warm interval, which is more than we expected. And more interestingly, there's also a strong seasonality or significant seasonality in the delta 18 of the seawater, which means that some other proxies that we might use, like stable oxygen isotope records, might be seasonally biased in this respect. And we can actually see that when we combine or compare our methods with model runs from the HAT-CM model. That's the image you see in the middle of the screen right here. And we see that actually a lot of these records are underestimating temperature, while or seasonal reconstructions actually fall quite well on the model, which is an interesting result. And it shows that we can actually use these type of seasonal records to learn a bit more about how other records may be biased, or also the kind of problems that arise when using certain archives that might have a seasonal bias or might be biased due to this problem with the composition of the seawater. Finally, I want to tell you something about what we're going to do right now. The next focus is on the Pliocene warm period, where there's a very nice large model compilation in existence. I'll be using the clumped isotope seasonality method together with 3 very excellent students that are just starting to look at these bivalves, very nice, well-preserved bivalves from this period, from the sands of Belgium and the Netherlands. And this result we will compare it with these model studies that are already there, this framework. And I hope to see, I'm excited to see whether the seasonal approach will actually give us some new information about what it was like in these warm periods. So more to be told about that later. And with that, I would like to thank you for your attention, and we'll take any questions that you have.